Good morning, radioactive half-life. So you can see down there SQA wanted to know what it's defined as and then how to calculate it using graphical or numerical data. So the first thing is I'm going to take you through just a very brief simulation here, which shows you the number of atoms in a radioactive sample. These ones are all red. They're all ready to lose their radioactivity, to emit alpha, beta, or gamma particles. I'm going to press play, and you can see that some of them change into other things. You're going to play around with that yourselves later, but that's what we're after here, the number that change from being originally as they were and then emit radiation and change to decayed particles. And as you can see, all of these have now decayed, which is quite unusual. So going back to slides here, you've got that kind of graph is always drawn out with this curve. So you start off with the initial number of your radioactive particles there, and the half-life is the time taken for half of the atoms of that radioactive element to disintegrate. So if we go from N0, which could have been 100, and if it went down to 50, that's half the initial number. That time measured along the time axis is the half-life. And you can do the same thing again. This, you can also have plotted here the activity of the source rather than the number of radioactive atoms. The same thing works, because what we've got here is got half of the initial number which we had before. If you half that again, you're going to end up with a quarter of that initial number. So if that was 100, that'd be 50, that'd be 25. The time now is double the half-life. You can see that the half-life is constant. It doesn't really matter what the actual sample size is or what the initial number, it'll just keep halving. Same thing again. This time going from maybe 25 down to 12.5, so that would be the initial number divided by 8. Each time we're halving, n divided by 2, n divided by 4, n divided by 8. This would be triple the half-life along the bottom here. In practice, it's a really random process, radioactivity, so you won't get a nice smooth curve with this. Quite often your points will be a little bit all over the place. You've just got to draw a smooth, best fit curve as best as you can if you have to do a graph. And quite often, if it's real data, it will never actually get to 0, so we can't measure the time that it takes for a radioactive substance to decay completely. That's why we need half-life. The units for half-life are any unit of time, so there's no time specified on this here because it's an arbitrary set of units. So what's up for the rest of this morning? I'd like you to have a go with that simulation. I'll give you the link on Google Classroom. You're then going to watch a video and plot a graph on Google Sheets. Again, the links are on Classroom, and the Sheets will plot the graph for you. Then you've then got to get the half-life of the source in the simulation here. You're then going to be shown how to do calculations based on numerical rather than graphical data, and then finally a set of questions from the folders, and that should take you most of this morning. If you get stuck, get back to me in a comment on the chat, but otherwise you should now be all ready to get started on half-life.